Hi, this is Ryo Shinohara from the online section of CSC 578, presenting my rather abysmal results of my final project. So this is the general overview of what I'm going to go over in my Jupyter Notebook. And to start off, we're going to take a look at a couple of exploratory data analyses that I did. And for that, I basically plotted several line charts for every variables available in this data set. And these sets of line charts, as you can see here, and two more over here, I have the temperature variable, which is the target variable for each of the plots, to make it easier to compare and contrast the independent variables. And quickly, you can see that the relative humidity, that is relative humidity. And then the atmospheric pressure right here, and the wind velocity down here doesn't follow the same cosine sine wave trend that you can see in the temperature variable and all other variables. But I kept it nevertheless. So moving on to the data pre-processing stage, for this I largely used Jason Brownlee's code from his wonderful website. Thank you, Jason Brownlee. And I've slightly modified it so that I can manually compute the denormalized y values with this get inverse function, rather than use the, I believe, inverse transform function from the scikit-learn package. Moving on to the gist of the neural network building, the first thing I did was to loop over different activation functions and different unit sizes in multiple attempts to see which hyperparameters are best for those two hyperparameters. And here are some helper functions for that. This is the reshape data function that reshapes the data to fit the LSTM layer. And then this is just a function to loop over the activation and the unit size variables, parameters. And so in my initial run, I ran through 30 epochs, going over 4 activation functions, which were tanh, sigmoid, ReLU, and softmax, over unit sizes from 10 to 100, going in steps of tens. And you can see the results in this line plot right here. And as you can see, this blue line tends to be performing much better than the other lines. And this blue line happens to be the sigmoid function. And so I decided to use the sigmoid function for further analyses. And actually, after I submitted my Kaggle competition results, I noticed that the models that I built using smaller epoch sizes tended to do better in my final y-hat MAEs, so I decided to reduce it even further to only 10 epochs per building network for my final networks. But in any case, let me just quickly see that this whole function is working, and it seems to be working fine. And this is a line plot of the 10 epoch neural networks using the sigmoid activation function, looping over unit sizes of 10 to 100 in multiples of 10. And the minimum appears to be around unit size of 80. And I slightly got curious as to whether it would improve with increasing the unit size. But as you can see from here, and scrolling a bit more down, doesn't improve it at all. So I kept the best activation function in all hyperparameters as so. So I used the sigmoid function, a unit size of the first LSTM layer as 80, and epoch of 10. Then moving on, I tried to tune the regularization. I used both L2 and L1, and the dropout layer. But these honestly did not improve the final MAE at all. It actually worsened it to even 4.1 compared to my earlier values, which were around 1.5. as seen here. So I decided not to include dropout or the regularizations in there. And then the next thing I tried to do is to find the best activation function for the dense layer, which was right here. And I used the 10H, sigmoid, ReLU, and softmax activation functions and looped over them. And I found that when I compared those four with the same hyperparameters otherwise, that ReLU performed the best as so. So I decided to use that for further analyses. And then I also tried to add another LSTM layer, but as you can see in my results right here, they actually worsened my results even further. So that left me with this relatively simple network of LSTM unit size of 80 using the activation function of sigmoid, and a dense layer of size 1 with the ReLU activation function. And unlike the results that we saw up above, it got even worse. The MAE is now 2.574. So unfortunately, my results weren't amazing, and there were definitely a couple of things that I would have liked to change in the future, such as not including some of those variables that didn't seem to follow the same trends, and perhaps changing my batch size parameters, tuning over different batch sizes, and perhaps taking averages of various networks with the same hyperparameters and taking the average of those to see which one would perform best. But overall, it was a very disappointing project. I hope your projects did much better than mine, and thank you for listening.